Welcome to the 17th video of the physics lecture series for the National Science and Mathematics Olympiad. In this video, we will discuss how to describe motion in two dimensions. The key to understand two-dimensional motion is the principle of independence of motion. It states that the motion along one axis, for example the x direction, is independent of the motion along a perpendicular axis, so the y or the z direction, provided the forces acting in these directions are independent. In other words, if the forces acting in the various directions are independent, we can treat the movement in the x and y directions separately. Of course, this could be extended to three dimensions as well, where you would have three independent movements. Consider the case of throwing a ball at an angle. Neglecting air resistance, there is no force acting on it horizontally, so the movement in that direction can be considered as a uniform linear motion. Gravity acts in the vertical direction, so the movement there will be a motion with constant acceleration. We will discuss this specific case in more detail in the next video, but for now, let's see the general principles. Preferably, we describe motion in two dimensions using vectors. The object starts at the position Ri and moves to the final position Rf. Using unit vectors, the initial position can be described as Ri equals xi times I plus yi times j. Similarly, the final position is xf times I plus yf times j. The displacement is simply the difference between the two vectors, so Rf minus Ri. Substituting the expressions for the final and the initial velocities, we arrive at xf minus xi times I plus yf minus yi times j. xf minus xi is simply the change in the x-coordinate, so it is delta x. Similarly, yf minus yi is simply the change in the y-coordinate, so it is delta y. Let's now see how can we express the average velocity vector. It is the displacement vector, so delta r, over the time elapsed, delta t. Substituting the formula we got for the displacement on the previous slide, we can express the average velocity vector with the unit vectors and the changes in the coordinates. It is important to see that the average velocity vector points in the direction of the change in displacement. And this is what we would have expected. We can treat the average acceleration vector very similarly. It is simply defined as the change of the velocity vector over time. Let's see an example. A camel is at the origin of the coordinate system at time t1 equals 0 second. For the time interval from 0 second to t2 equals 12 seconds, the camel's average velocity has an x component of minus 3.8 meters per second and a y component of 4.9 meters per second. At time t2 equals 12.0 seconds, the question is A, what are the x and y coordinates of the camel, and B, how far is the camel from the origin? To solve this problem, we have to remember the principle of independence of motion. So we can treat the movement along the x-axis and along the y-axis separately. Starting with the movement along the x-axis, x2 equals x1 plus vx times t2 minus t1. So x1 was simply 0, and then we substitute the values for vx and the time difference, and then the result, the x2 coordinate, is minus 45.6 meters. Then along the y-axis, y2 is equal to y1 plus vy times t2 minus t1. Again, y1 was 0, and then we just substitute vy and the time difference here, and then the result is 58.8 meters. Therefore, the final position described by the x and y coordinates is minus 45.6 meters and 58.8 meters. Part B asked for the distance of the camel from the origin. We can calculate this using the Pythagorean theorem, using the final coordinates that we just calculated. So r is equal to the square root of x2 squared plus y2 squared. So just plugging in the numbers, we can get the final result of 74.4 meters. Finally, let's talk about two-dimensional motion with constant acceleration. For this, we have to remember the 5 equations of motion discussed in video 13. Then we simply apply the principle of independence of motion. This means that we have the exact same 5 equations as we had in video 13, but specified in each direction. So these are the 5 equations of motion of the movement along the x-axis. And for the y-axis, you would use the exact same equations, just changing each x to y in all of them. Thank you for your attention and see you in the next video.